And we're going to move on now to our next speaker, Irene Calvo Almazan. Irene Calvo is a scientist in the Interfacial Processes group at Argonne, and she's developing new experimental approaches and algorithms to apply coherent X-rays to the in situ study of the reactivity of relevant mineral water interfaces in the context of the geosciences. So the title of Irene's talk is Leveraging X-ray Coherence to Probe the Complexity of Realistic Mineral Water Interfaces. And Irene, it looks like you're pretty well set up here.
Okay, so thanks for the introduction. I assume that you can see my slides.
Yep, go on.
Okay, so thanks a lot as well to the organizers for inviting me to talk today about, well, the new opportunities for coherent X-ray techniques that are offering new synchrotrons, specifically to the study of complex and realistic mineral water interfaces. So let me start by clarifying what we mean by complexity with three examples. The first one is this 3D dissolution rate map of a micro-sized calcite crystal, where you can see how edges dissolve much faster than the flat facets of the crystal. The second example is about these complex morphology islands of cadmium carbonate grown on a calcite 104 substrate. And one of the questions is how the underlying topography of calcite, its steps, its defects, determines the position where these islands nucleate and also their morphology. And the third example is about the coexistence between different reactive pathways, like here, where you can see the co-growth of calcite and vaterite, two different phases of calcium carbonate. So complexity is this interplay between structure, morphology, and dynamics. And these three examples illustrate how they strongly impact the reactivity of the interfaces. So to disentangle this 4-4 relation, we need to find a probe which enable us first to follow processes which take place in a very wide range of length scales, like from nanometers to micrometers and in 2 and 3 dimensions. We also need a probe which is sensitive to interfaces and also dynamics at interfaces. And third, we need a probe which can observe metastable phases and therefore can penetrate in situ environments. So for all these reasons, we think that coherent X-rays are potentially a very interesting probe to analyze these processes. And an example is given here of the informational content provided by coherent X-rays with this in situ study of a calcite water interface. So if we do some reflectivity measurements of this interface and we look at the intensity, which is diffracted at the anti-Bragg position, which is this position in the reciprocal space, which is so sensitive to the interface structure. If we use a standard X-ray beam for these measurements, we observe that the intensity, which corresponds to a section of the crystal truncation rod. So the crystal truncation rod gives us information in average about the size of the domains on the interface. So more specifically, its width is related to the average size domain. However, if we use a coherent X-ray beam to do the same sort of experiment, we observe in the detector that the CTR this time is decorated by what we generically call speckles, but here are proper fringes. And the geometry of these fringes is very exactly related to the morphology of these domain islands. Actually, is related by a Fourier transformation. So therefore, with coherent X-rays, we can observe the exact topography of the interface. But coherent X-rays can also be used to observe complex 3D interfaces, like this 3D nanometric calcite rhomb in contact with a liquid solution, which is in this fluid cell. And so if we illuminate the sample with a coherent X-ray beam and we place our detector in such a way that the geometry of the scattering matches the momentum transfer for the 104 Bragg peak reflection of calcite, we can see that our 2D detector plane cuts the 3D distribution of intensity around this specific Bragg peak. And this is the image that you can see in the detector is a 2D speckled pattern. And once again, you recognize these fringes whose geometry corresponds to the Fourier transformation of the rhomboedrical morphology of the calcite rhomb. Now, the question is, how can we access, Yeah, how can we access the 3D information which is encoded in this speckle pattern? Well, we need to perform a rocking curve scan around the 104 Bragg peak, which consists in rocking in changing slightly the orientation of the crystal with respect to the direction of the incoming beam in order to sweep the 2D plane of the detector across the diffraction, the diffracted intensity in such a way that we obtain a series of slices of this 3D speckle pattern around the Bragg peak, and from which we can use an algorithm to obtain a proper 3D image of the diffracting crystal. But it's a very special image because it's also sensitive to defects and any crystalline distortion, which is encoded in the face, represented in the face of the object, which is represented here as a color map. So this approach is called coherent diffraction imaging, or CDI, and it can be used, as we have seen, to observe 2 and 3D structures and morphologies, reaching nanometric resolution encoded in the complex phase, and which can be used to observe crystals whose size range from hundreds of nanometers up to 1 micrometer, and even larger systems with tychography. And in essence, it's a microscopy technique. Now, in current synchrotrons, CDI can be used, for instance, to map the 3D strain and defects of nano-sized crystal, like these nanomagnetite crystals, which have been partially dissolved. Or as I mentioned before, with tychography, we can map in 3D the stacking faults and the strain of semiconductors wires, which are in the micrometer length scale. We can even use coherent X-rays to observe dynamics, and this is a technique which is called X-ray photon correlation spectroscopy, XPCS, and which consists in monitoring the fluctuations of the speckles over time at a specific point of the reciprocal space, like in this example at the anti-Bragg of a titanium oxide surface during step flow growth. So, and the goal is to extract the time correlation of these speckles at different length scales in order to identify the mechanisms which govern the dynamics of the steps. Now, in new synchrotrons like the APSU, we will have between 2 and 3 orders of magnitude gain in coherent flux. So this will enable us to increase the scattering from interfaces, perform faster measurements, and a higher spatial resolution, which will expand importantly the window of length and time scales which can be observed with coherent X-rays. But very importantly, this gain in coherent flux will also happen at high energies, which will increase the penetration length of coherent X-rays and therefore broaden significantly the collection of in situ conditions that can be accessed with coherent X-rays. Last but not least, we will also benefit from small beams, which will enable these multi-scale measurements. So with the advent of these new synchrotrons in the horizon, we need a strategy to leverage coherence and reach our ultimate goal, which is to perform operando studies of crystals which are dynamically evolving. So for that, we have identified 2 complementary directions: structural complexity and dynamical complexity. And from the gain in coherent flux provided by APSU, we will already be able to observe, for instance, stationary dynamics and slow kinetic evolution at flat interfaces, and also 3D nanocrystals in contact and equilibrium with a liquid solution. But eventually, to perform these operando studies on dynamic crystals, we will need to improve the algorithms and the experimental approaches. So in the next few slides, I'm going to show 2 examples of how we are implementing this strategy in our research. The first example is about thin film morphology studies using coherent X-rays in anticipation of the new capabilities at APSU. And the second example is about some advances in the conceptual framework, which enable us to retrieve structures directly from a coherent diffraction pattern. So let's start by the coherent X-ray reflectivity studies of thin film morphology. where we have chosen the system of cadmium carbonate, also known as otavite, grown on dolomite 104 substrates. So we have chosen this system, first of all, because otavite is a very strong scatter, as you can see by in its very intense thin film Bragg peak. But also using in situ X-ray reflectivity, we have discovered that there's an interesting coupling between the epitaxial strain in the thin film, given by the position of the thin film Bragg peak, and different stages of the growth of the film. So this system presents a really interesting interplay between strain, dislocations, and growth mode, which makes it worth to study with coherent X-rays. And furthermore, it is an excellent proxy to prepare future real 2D interface studies with coherent X-rays in new synchrotrons. So what can we learn with coherent X-rays about thin film morphology? So, well, we have performed measurements at sector 12 at APS, where we used a micrometric coherent X-ray beam to illuminate an otavite film grown on dolomite. And in this particular scattering geometry, the detector plane is intersecting simultaneously a section of the thin film Bragg peak and of the crystal truncation rod arising from the scattering of the interface between the film and the dolomite substrate. And here is a corresponding to the detector image, where you can see that while the thin film Bragg peak presents a very wide broad distribution of intensities with lots of speckles, the scattering of the CDR is almost reduced to one single pixel with fringes. So this already suggests that the morphologies of the otavite and the dolomite will be very different. Now, if we want to gather 3D information, we need to perform a rocking curve scan. So we need to swap across the otavite thin film distribution intensity the plane of the 2D detector. And we will do this by changing the orientation of the sample with respect to the direction of the incoming beam by very small angular steps. And in this rocking curve scan, we will collect a series of 2D slices of the otavite film Bragg peak, where you can see in these examples how the CTR progressively merges with the thin film Bragg peak until it completely disappears when the momentum transfer corresponds to the 104 thin film Bragg peak, and then continues its trajectories once we have overpassed it towards the dolomite 104 Bragg peak. So the interesting thing is that with this set of 2D slices, we can construct a 3D map of the reciprocal space. So let's have a look to some of the cuts of this reciprocal space volume. So the first cut is along a plane which is parallel to the CTR, the HL map. And here it's interesting to compare an HL map measure with coherent X-rays with an equivalent map, but measure with a standard X-ray reflectivity. Because once again, while standard X-ray reflectivity gives us information about the average morphology, so for instance, we can extract the centroid of the thin film Bragg peak and deduce the epitaxial strain. We can extract the average size of the domains by extracting the width of the thin film Bragg peak. The coherent X-ray map is much richer in terms of structural information. So in particular, in this case, you see these elongated speckles. So the lateral position of these speckles is, and its elongated shape parallel to the CTR reveals the strong connection, the strong correlation between the thickness of the domains and their lateral size within the illuminated volume. Now, another cut of the reciprocal space, which is interesting, is the HK map, which is parallel to the film plane. And here, if we look at an HK map with coherent X-rays for a otavite and dolomite sample, we observe that we have a very wide distribution of speckles, which arise from the lateral distribution of lateral sizes of the otavite domains. And simultaneously, we also see the contribution of the underlying dolomite through the CTR, which once again is very narrow. And these fringes that we can distinguish, which correspond to the existence of steps. And what is interesting is then to compare this HK map for an unreacted dolomite substrate, where once again, we observe that the CTR is very narrow because indeed, dolomite consists in very large and smooth domains, and steps which create these fringes in the reciprocal space. So now what you would expect is the third and last step, which is to invert this 3D reciprocal space volume to obtain a 3D exact topography of the thin film and the substrate with sensitivity to strain dislocations and defects. But this is work in progress, and it's the step that we need to perform. So unfortunately, I can't show you the results. And for doing this inversion, crucially, we need to design an algorithm. So talking about algorithms leads me to the second part of my talk, which are these conceptual advances that we have performed to address what we call the phase problem, and to devise, which enables us to devise a strategy to retrieve structures directly from a coherent diffraction pattern. But let's start by recall what is the phase problem. So the phase problem states that if we have a structure that we illuminate with an incident coherent X-ray beam, and we record with a 2D area detector the diffracted intensity. So from this coherent diffracted intensity, where you can see the speckles, we cannot directly infer or retrieve the structure. And the reason is that what we are measuring are intensities, so which correspond to the modulus square of the diffracted wave field, which is a complex diffracted wave field and consists on a modulus and a phase. Therefore, if we want to retrieve the structure, we need to retrieve the phases. And for this, we traditionally use a phase retrieval algorithm. So the most common phase retrieval algorithms are based on the error reduction strategy. So these are iterative algorithms whose goal is to minimize this function that we call the error metric, which is the difference between the experimentally measured diffraction patterns and a set of calculated diffraction patterns from a guessed object. So the goal of the algorithm is through the successive iterations to find the global minimum of this error metric. And this is how the error metric evolves with 5,000 iterations of one of those algorithms. So we assume that when we reach a plateau, we have found the global minimum, and therefore the object which minimizes the error metric, which should correspond to the diffracting object. However, these algorithms have shortcomings. They have lots of local minima, and especially when we have real experiments, we have noise. It's very difficult to guarantee that we have reached the global minimum. This is why we are looking for a strategy from which we can retrieve a structure from the coherent diffraction pattern, but without bypassing this sort of algorithms. And we took inspiration in Fourier holography. So Fourier holography consists in the following. Imagine that we have a sample, this A is the sample, and a point-like reference. And we illuminate this object with a coherent X-ray beam. So we measure the diffracted intensity, and then we take the Fourier transformation of this intensity to obtain a holographic image, which contains a direct image of the sample and an antisymmetric image, and then an autocorrelation term. So in Fourier holography, there's no need of an error reduction phase retrieval to have a direct image of the sample. So the question is if we can apply the same method to the coherent diffraction patterns. So imagine that we have these 5-atom samples, and we illuminate it with a coherent X-ray beam to obtain this coherent diffracted intensity. Now, what happens if we take the Fourier transformation of this intensity? So we obtain what we call the Patterson function, which consists on a central spot and a series of peaks. And the different peaks are connected to the central spot through vectors, which corresponds to interatomic vectors in the structure. Now, if we look more closely, the inner structure of the Patterson function, we discover that it consists on a series of copies of the original structure, where each one of the atoms act as a reference. For instance, in this red copy, the first atom acts as a reference and is in the middle. In this green copy is the fourth atom, which acts as reference and is in the middle. In other words, the Patterson function is an autohologram of the structure, and it contains, in this case, 5 direct images of the structure. So in general terms, it contains, if the structure consists of n atoms, it contains n direct images of this structure. So we have tested the performance of the algorithm with non-trivial systems, like this example where we combine a mixture of periodic and non-periodic array of atoms with different scattering factors, which are symbolized by different markers with different colors. And so this is the corresponding diffracted intensity, and the algorithm is capable to retrieve from the 650 peaks of the Patterson function, one out of the 26 copies which the Patterson function consists of. And as you see, the algorithm not only retrieves the position of the atoms, but also the scattering factors, so the identity of the atoms. We have also tested these algorithms with a system consisting of 100 atoms with random positions. And so the algorithm successfully retrieves one of out of the 100 copies which form the Patterson function. So to conclude, in this talk, I've shown you a strategy to leverage coherence in order to reach our ultimate goal, which is to perform operando studies of crystals under realistic conditions. And so one of the examples is about using thin films as a proxy for 2D interface studies to prepare future 2D interface studies with coherent X-rays at new synchrotrons like APSU. And I've also shown you some advances in conceptual advances to develop new strategies to extract very efficiently structural information from CDI patterns. So thank you very much for your attention. You are muted, Peter, sorry.
It had to happen once. Thank you so much, Irene. That was really a fascinating look into the future. Song-Soo has asked a question. Can you briefly mention what new capabilities the APSU will bring to us and when it will happen?
Yeah, so, well, when it will happen, it will be probably so in 2 years. I think that in 2022, no, the upgrade was planned for the spring of 2022, if I'm correct, and I think it has been delayed by 1 year due to the pandemics. So probably APSU will be online maybe in 2024, I think. And so the new capabilities will be specifically this gain in coherent X-ray flux between 2 and 3 orders of magnitude. The fact that we will have a gain in coherent flux not only for low energies, but also for high energies, which is very important for in situ studies. And also the fact that we will benefit from very small beams. So these will enforce these multi-scale measurements because it will enable, it will favor tychography and all these raster scan methodologies.
And I don't know if you just saw in the chat that Mark Rivers clarified that it will go down in June 2023, come back a year later.
Oh, yeah. Okay. Thank you.
Okay. Any other quick questions for Irene? Okay, well, it's 7:30 your time, so have a good evening and thanks so much for that contribution. It's really fascinating.
Thank you.